A doctoral student stares at satellite data showing an impossible number. The Greenland ice surface dropped 85 meters in 10 days. Her instruments are fine, the data is real, and it shouldn't exist. Not in a region every model declares frozen solid to the bedrock. But what Pentagon imagery would soon reveal beneath that ice was even harder to explain. While Jade Bowling was wrestling with one impossible event, 3 more discoveries were quietly emerging, and together they may rewrite everything we think we know about what is happening under Greenland. Jade Bowling's screen glowed with numbers that should not exist. 85 meters, gone in 10 days. The ice surface dropped by the height of a 28-story building over an area the size of 200 football fields. Not a slow sag, not a seasonal dip, a vertical plunge as if the ground itself had vanished beneath the ice. The first instinct was a glitch. But the instrument logs were clean. She wrote in the telemetry notes time-stamped July 7th that her instruments were fine. Receiver gain was steady, and temperature was holding at -5. No dropouts, no warnings. The raw radar altimeter files archived in the Lancaster University data vault matched the satellite passes to the second. Every pixel, every reading was consistent. She called in her supervisor, Malcolm McMillan. His verdict landed hard. "We have not seen this before." The phrase stuck. The event was not a rumor or a math error. The Pentagon's own SAR frames released weeks later captured the collapse in 5-meter detail. Chain of custody logs, cryptographic hashes, downlink times, all verified. The U.S. National Geospatial-Intelligence Agency certified the images. The surface had dropped, and the crater was real. Independent data streams piled on. Sentinel-1 interferograms showed the deformation. Cryosat-2 and ICSat-2 altimetry measured the vertical loss, 85 meters, confirmed from 3 angles. Arctic DEM photogrammetry, Tandem X radar, even Maxar Worldview 3 optical shots, all aligned. No single instrument, no single analyst. A chorus of sensors, all telling the same impossible story. Within that 10-day window, the numbers refused to bend. A surface drop of this magnitude should take centuries. Here, it happened between satellite overpasses. The chain of evidence was locked. The anomaly was real. What lay beneath was no longer just ice, but a question tearing open the floor of what science thought it knew. Organizations go quiet when the data is moving faster than the frameworks built to explain it. Greenland, it turns out, may be running on an old version of itself. The only certainty now, the ice is not waiting for anyone's model to catch up. Greenland sits more than 2,000 miles from the nearest major city, but its numbers hold the keys to the world's future coastlines. Every year, satellites tracking the ice sheet's mass loss deliver a single, unblinking figure, 264 gigatons. That single figure is the official baseline, 264 gigatons of ice gone each year, according to Grace-Fo satellite gravimetry. Not a guess, not a projection. A direct measurement, written into the ledgers of climate policy and infrastructure planning from New York to Shanghai. But a number like that is never just a statistic. It is the foundation for every flood map, every seawall budget, every insurance calculation for a city within reach of the tides. The 264 figure feeds into the algorithms that set FEMA's floodplain boundaries and the European Union adaptation codes. It underpins the risk models used by the World Bank and the actuarial tables that decide whether a city can borrow for a new subway line. When planners look to the future, they are looking through the lens of Greenland's melt rate. The ultimate ceiling is even starker. If Greenland's ice sheet ever fully collapses, the world's oceans will rise by 24 feet. Not centimeters, not inches, 24 feet. That is enough to redraw the map of every coastal nation, enough to swamp the heart of London, erase entire neighborhoods in Miami, and push salt water into the subways of New York. The 24-foot figure is not a fantasy. It is a line written in every major climate assessment, a silent threat hanging over 1 billion people worldwide. Yet all of these projections, all of these plans, rest on the assumption that Greenland's behavior is understood, that the ice sheet is slow, predictable, and governed by rules scientists have already mapped. The models are only as good as the numbers they feed on. If the ice moves in ways the models cannot see, if the ground under Greenland is rewriting the script, then the world's most trusted forecasts could be off by feet, not inches. Organizations go quiet when the data is moving faster than the frameworks built to explain it. The question is no longer just how much ice is lost, but whether anyone truly knows how much will reach the ocean, how fast, and when. Deep inside the Greenland ice sheet, the numbers started breaking the rules. For decades, every major forecast, every flood map, every engineering code rested on a simple assumption that deep ice moves like cold molasses, slow and stubborn, with a stiffness measured in the thousands of trillions of Pascal seconds. But in February 2026, a team from the University of Bergen published results that upended that foundation. Their simulations, built on radar scans and vertical temperature profiles, refused to match reality unless the deep ice was made 10 times softer than anyone had dared to model. Not 10% softer, not twice as soft, 10 times. The equations at the heart of every ice flow model, Glen's law, the constitutive backbone of glaciology, depend on a single multiplier, the softness parameter A. In textbooks, A is locked down by lab tests and Arrhenius curves mapped against temperature and chemistry. But when the Bergen group ran their convection code, aspect, using the standard numbers, the simulated ice stayed rigid and flat. Only when they dialed up A by a factor of 10 did the model start to match the wild plume-shaped distortions seen in radar. The deep ice, they found, was behaving more like warm taffy than ancient stone. This is not a tweak. In the model, a 10-fold jump in softness means the stress needed to move the ice drops by more than half. Ice streams accelerate, basal sliding takes over, and the entire velocity pattern of Greenland's outlet glaciers shifts by tens of kilometers. Model runs with the new multiplier-produced sector, speeds up to 120% faster than before. A single parameter, out of place by one order of magnitude, can swing sea level forecasts by centimeters, even inches, by the end of the century. The Bergen paper called the discovery as wild as it is fascinating. The numbers forced a confrontation. Are the world's ice sheet models running on an old version of Greenland, one that never included deep convection or accounted for ice that can organize itself, flow, and fail at rates no one planned for? Organizations go quiet when the data is moving faster than the frameworks built to explain it. The question now is not just why the ice is softer, but what else the models are missing, and how far the error might reach. Beneath nearly a kilometer of Greenland's ice, a hidden lake erupted. 90 million cubic meters of water forced upward in a single violent surge. That is the equivalent of Niagara Falls running for 9 hours, but instead of plunging down, the water blasted up, tearing a crater 85 meters deep. The rim was littered with ice blocks the size of small buildings, some stretching 25 meters across. No gradual seepage, just a hydraulic fracture, water pressure punching straight through the ice, defying every prediction. Within hours, the Pentagon image validation team mobilized. Synthetic aperture radar frames, each stamped with cryptographic hashes and chain of custody logs, captured the event with 5-meter resolution. Every image, every timestamp, every transfer was verified and certified by the National Geospatial Intelligence Agency. The dataset included downlink times, ground station handoffs, and SHA-256 hashes locking in the evidence. The images revealed what no model had unimagined. Sentinel-1 interferograms showed the ice flexing outward, a ring of deformation radiating from the breach. Cryosat-2 and ICSat-2 altimetry confirmed the vertical loss, 85 meters, measured from 3 independent sources. Arctic DEM and Tandem X radar mapped the crater's contours to within 2 meters. Even high-resolution optical shots from Maxar's Worldview 3 picked out fresh ice blocks scattered across the surface, debris from a blast. Hydrofracture theory says when water pressure at the base surpasses the weight of the overlying ice, cracks can shoot upward at meters per second. But 90 million cubic meters, an entire subglacial lake forced through 900 meters of ice, was supposed to be impossible. The energy rivaled a small hydroelectric dam's annual output. Seismic tremors echoed for days, a low, rolling signature of fracture propagation. The Pentagon chain of custody protocol left no room for doubt. The event shattered assumptions about what Greenland's ice can do. If the ice sheet can fracture upward and eject water and blocks on this scale, the old models are incomplete. The rules have changed. Radar slices cut through Greenland's interior, revealing what looks like smoke rising inside solid ice. These are not artifacts, these are vertical plumes, columns of ice, tens of kilometers tall, twisting upward from the base. The shapes match nothing in the textbooks. Standard ice flow models built on Glenn's law insist the deep sheet should be static, slow, and cold, an ancient mass locked in place for millennia. But the radar plumes refuse to vanish. They show motion, they show heat. And when the University of Bergen team ran their aspect convection model, the numbers only lined up when they made the ice 10 times softer than anyone had dared to imagine. Not 10% softer, not twice as soft, 10 times. The Bergen lead summarized it in a single line: the discovery is as wild as it is fascinating. Their simulation produced rising, swirling plumes inside the ice, mirroring the radar patterns exactly. It wasn't a tweak, it was a rewrite. Deep ice, it turns out, can organize itself, convect, and flow like warm taffy, not ancient stone. This is not just about softness. When the ice is that compliant, stress travels differently. Forces that would have once dissipated over centuries now ripple upward in days. The surface collapse, the explosive lake drainage, the impossible speed all become possible when the rules change at depth. The implications reach far beyond the ice sheet. A tenfold jump in softness means the velocity of outlet glaciers can leap by over 100%. The entire mass balance of Greenland, every number used to project sea level rise, begins to shift. Suddenly, the models that planners rely on are running on an old version of Greenland. The ice is not waiting for anyone's framework to catch up. As the Bergen team's visuals spread through the community, the message was unmistakable. Greenland's interior is not a frozen monolith, but a system capable of organizing itself, breaking free, and moving in ways no one predicted. Organizations go quiet when the data is moving faster than the frameworks built to explain it. Gravity and seismic surveys peeled back the ice, exposing a Greenland that does not match the maps. Beneath the surface, the bed is not a flat, featureless plain. It is a broken mosaic, 3 vast geological provinces, each with its own signature and none recorded in the standard models. The mapping effort pulled together data from NASA, Durham, Columbia, and Princeton, stitching airborne gravimetry, magnetotelluric lines, and radar profiles. The result is a revelation. Parallel valleys, spaced like the teeth of a comb, run for more than 150 kilometers beneath the headwaters of the Petermann Glacier and the northeast Greenland ice stream. The valleys are straight, regular, and deep, cut into bedrock that does not match any known rock type in the region. Dr. Paxman of Durham University put it bluntly: these are as yet unknown geological provinces. Their regular parallel valley morphology is unlike any glacial erosion pattern we have documented. Standard ice sheet models treat the bed as a static control surface, a passive boundary. But the seismic velocities, magnetic signatures, and density anomalies tell a different story. The ground itself is fractured, segmented, and layered in ways that could channel water, focus heat, or set the stage for sudden movement. The old frameworks assume the bed is mapped and its influence constant. The new data say otherwise. The spatial arrangement of these provinces means the ice above them may accelerate or stall depending on the hidden architecture below. In places, the valleys run so straight and so evenly spaced that glaciologists compare them to tectonic fault blocks, not river-cut canyons or glacial troughs. The models never saw them coming. Every new survey adds another layer of complexity. The bed beneath Greenland is not a blank slate. It is a system of controls and triggers waiting to be understood. The question is no longer just about the ice above, but about the engine below. How much of Greenland's future is written in the bedrock no model has ever captured? Deep beneath Greenland's ice, the story does not end with hidden lakes or unmapped valleys. In December 2025, a modeling team at the University of Ottawa ran a different kind of simulation, one that did not just look at the ice, but at the bedrock heat rising into it. Their 3-dimensional geothermal model mapped the temperature field under the ice sheet in unprecedented detail. The result was pockets of heat, far hotter than the surrounding crust, clustered beneath major outlet glaciers. These were not scattered anomalies. They formed a pattern, localized hotspots, some tracing a faint line back toward the Icelandic plume, others isolated like embers in a frozen hearth. The Ottawa team's thermal inversion results did not just add another variable, they supplied the missing energy. In places, the modeled heat flux exceeded 120 milliwatts per square meter, double the background level for the region. That is enough to keep the base of the ice at the melting point, even when surface temperatures plunge to -30. The effect is surgical. Where the heat pockets align with the deep valleys mapped by seismic teams, the ice above softens, basal water pools, and subglacial lakes become possible, even inevitable. This is not background warmth. It is focused energy, rising from the crust, reshaping the physics of the ice from the bottom up. The Ottawa model explains why convection plumes appear where they do, why deep ice can move like warm taffy, and why a lake can drain upward with the force of Niagara Falls. It closes the physics trilogy: soft ice, fractured bedrock, and now a hidden engine of heat. The ice sheet is not just melting from above, it is being organized, softened, and destabilized from below by a bed that refuses to stay cold, mapped, or still. The question is no longer what is under Greenland, but how fast that hidden heat can rewrite the world's coastlines. In the span of just 18 months, the pace of discovery in Greenland leapt from anomaly to upheaval. July 2025, the Pentagon's public release of synthetic aperture radar images, time-stamped and chain of custody certified, landed in the open, evidence of the impossible surface collapse. August 2025, the first preprint linking the crater to a subglacial lake eruption circulated through academic servers, drawing in teams from Lancaster, Bergen, and Ottawa. December 2025, the Ottawa group published their three-dimensional geothermal model, mapping concentrated heat pockets beneath the ice. Then February 2026, the Bergen team's convection paper landed, forcing the tenfold softness multiplier into the conversation and echoing through every ice sheet modeler's inbox. 4 dates, each a domino toppling the next. The story does not pause. Each release triggers a new round of questions, reanalysis, and hurried recalibration. The frameworks built to explain Greenland are now racing to keep up with the data pouring out of the ice. Institutional silence is not just a pause, it is a pattern. Policy agencies tasked with safeguarding the future find themselves outpaced by the very phenomena they are meant to monitor. The frameworks that shape coastal defense budgets and insurance risk tables still rely on numbers drawn from a Greenland that no longer exists. A senior planner, when pressed for comment, offered only this: "We await further guidance from the scientific community." That guidance, it seems, is still circling in preprints and embargoed reports, not in the hands of those setting the rules. The Sustainable Governance Indicators portal tracks pledges and progress, but nowhere do new findings about soft ice or hidden heat flux appear in the latest adaptation codes. Behind closed doors, the refrain is familiar. Organizations go quiet when the data is moving faster than the frameworks built to explain it. The question lingers, unanswered. How many more unknowns are locked beneath the ice? And how long can policy wait for certainty that may never come? Organizations go quiet when the data is moving faster than the frameworks built to explain it. Macmillan says we have not seen this before. 10 times softer. A heat pulse rivaling Niagara Falls. Geological provinces still as yet unknown. The stakes: 24 feet of global sea level rise. The models are running on an old version of Greenland. The question is not if the ice will move, but how much, how fast, and when. What do you think?